Good day, class. We are the group 6 and we will be discussing our topic about vibration measurements and applications. These are the members: Apple Grace Antimaro, Corinne Antimaro, John Navajo, Pauline Bedrio, and Romulo Tiras. Why we need to measure vibration? This is to detect shifts in angular velocity n, which indicates possible failure, to select operational speed to avoid resonance. Measured values may be different from theoretical values, to design active vibration isolation system, to identify mass, stiffness, and damping of a system, to verify the approximate method. Types of vibration measuring instrument used will depend on respective range of frequency and amplitude, size of machine or structure involved, condition of operation of the machine or structure, or type of data processing used. Transducer, a device that converts variation in a physical quantity such as pressure or brightness into an electrical signal, or vice versa. Variable resistance transducers are one of the most commonly used types of transducers, also called as resistive transducers or resistive sensors. They can be used for measuring various physical quantities like temperature, pressure, displacement, force, vibration, etc. These transducers are usually used as the secondary transducers, where the output from the primary mechanical transducers act as the input for the variable resistance transducers. The output obtained from it is calibrated against the input quantity and it directly gives the value of the input. Next is the piezoelectric transducers are a type of electric acoustic transducer that convert the electrical charges produced by some forms of solid materials into energy. The word piezoelectric literally means electricity caused by pressure. Next is the LVDT transducer or linear variable differential transformer. It is a commonly type of electromechanical transducer that can convert the directly linear motion of an object to which it is coupled mechanically into a corresponding electrical signal. LVDT, linear position sensor are readily available that can measure movements as small as few millionths of an inch up to several inches, but are also capable of measuring position up to positive negative 30 inches or positive negative 0.762 meters.
Vibration pickup. Vibration pickup is referred to a sensor for measuring vibration such as displacement, acceleration, and velocity. And the vibration pickup types are vibrometer. Vibrometer is the one that measures the displacement. Accelerometer, the one that measures the acceleration. And velometer is the one that measures the velocity. Next one, frequency measuring instrument. Single reed instrument or Fullerton tachometer. This is a clamp and pass against vibrating body. Adjust I until 3 shows largest amplitude of vibration. Second frequency measuring instrument is multi-instrument or tachometer. Clamp and press against vibrating body. Frequency read directly off strip whose free and shows largest amplitude of vibration. Frequency measuring instrument. Stroboscope produces light pulses. A vibrating object viewed with it will appear stationary when frequency of pulse is equal to vibration frequency.
To determine dynamic characteristics of machine structures and fatigue testing of materials. 3i vibration exciters is a machine which produces mechanical vibratory motion to test object. It is designed to produce a given range of harmonic or time dependent to produce excitation force and displacement through a given range of frequency. Type of exciters. There are three types of exciters commonly used in several applications are mechanical exciter, electrodynamic exciter, hydraulic exciter. Mechanical exciter, which vibrates the structure or machine by mechanical system. There are three types of mechanical exciter: inertia force mechanical exciter, elastic spring force mechanical exciter, unbalanced force mechanical exciter. Inertia force mechanical exciter, force applied as an inertia force, Scotch yoke mechanism used to produce harmonic vibrations. It is used to apply harmonic force. Elastic spring force mechanical exciter, force applied as elastic spring force, Scotch yoke mechanism used to produce harmonic vibration. It is also used to apply harmonic force. It is also generally used for frequency less than 30 Hz and load less than 700 Newton. Unbalanced force mechanical exciter. Force is applied as rotating unbalanced mass. The rotating unbalance generates an oscillation force which vibrates structures or machine. It is used to generate relative large load between 250 and 25,000 Newton. Advantage of mechanical exciters is generate force are transmitted directly to the table without dependence upon a reactionary force against a heavy base or rigid ground connection. Cost of mechanical exciter is less compared to other exciter. There are no leakage problem as in hydraulic exciter. Defective electrical component and connection fail under the induced vibration. This exciter eliminates embarrassing and costly repair and difficult tracing in circuits in the field. Disadvantage of mechanical exciter. Mechanical exciter cannot be used in high temperature, humidity, and altitude environments. It can only use for small application, and frequency range is small compared to the hydraulic and pneumatic. Electrodynamic exciter. It is also known as electromagnetic exciter. Electrodynamic force applied to vibrate the structure. The magnitude of acceleration of the component depend on maximum current and masses of component and moving elements. It generates force up to 30,000 Newton and displacement of 25 mm. The operating frequency range of the exciter lies between 5 to 20 kHz. Advantage: it can produce purely harmonic and constant force. It can use wide frequency range, easily measurement the excitation force. Disadvantage: it has a great mass and volume with respect to amplitude of the generating exciting force. Electrohydraulic exciter. Fluid pressure is used as power source of hydraulic vibration exciter. In this arrangement, an electrically actuated servo valve operates a main control valve, in turn regulating flow to each end of a main driving cylinder. Large capacity up to 2 meganewton and relatively high frequency to 400 Hz with amplitude as great as 46 mm has been attained. This is the comparison of exciter. Mechanical exciter has frequency of 2 to 50 Hz, maximum displacement of 2.5 cm, maximum acceleration of 20, maximum force of 4,500 Newton, excitation waveform of sinusoidal only. Electrodynamic has frequency of 2 to 10,000 Hz, maximum displacement of 2.5 cm, maximum acceleration of 100, maximum force of 2,000 Newton, excitation waveform of high flexibility and accuracy. In electrohydraulic, it has a frequency of 0.1 to 500 Hz, maximum displacement of 50 cm, maximum acceleration of 20, maximum force of 450,000 Newton, excitation waveform, average flexibility. Signal analysis. In signal analysis, we determine the response of a system under a known excitation and present it in a convenient form. Often, the time response of a system will not give much useful information. However, the frequency response will show one or more discrete frequency around which the energy is concentrated. Since the dynamic characteristic of individual component of the system are usually known, we can relate distinct frequency component of the frequency response to specific component. The first picture shows us acceleration time history of frame subjected to excessive vibration. The second picture represents us transformed to frequency domain. Spectrum analyzer separates energy of signals into various frequency bands. Real-time analyzer useful for machine health monitoring. There are two types of real-time analysis procedure. Digital filtering method, fast Fourier transform method. The basic component of spectrum analyzer is bandpass filter. Bandpass filter is a permit passage of frequency over a band and rejects all over the components. Picture shows us response of a filters. Frequency up and frequency lower cut off frequency respective to frequency center. Ripples within the band is minimum for a good band filter. There are two types of band filter, constant percent band filter and constant band filter. Constant percent. Frequency up minus frequency lower over frequency center is constant. Octave 1/2 octave filter, constant bandwidth. Frequency upper minus frequency lower is independent of frequency center. Constant percent of bandwidth and constant bandwidth analyzer. Spectrum analyzer with a set of octave and 1/3 octave band filter can be used for signal analysis. Lower cut-off frequency of a filter upper cut is equals to upper cut-off frequency of previous filter. Filter characteristic as shown in the picture. Constant bandwidth analyzer is used to obtain detailed analysis than constant percent bandwidth analyzer. Wave or heterodyne analyzer is constant bandwidth analyzer with continuous varies center frequency.
Good evening, everyone. My report is all about dynamic testing of machines and structures. So, dynamic testing of machines and structures, it involves finding the deformation of machines or structures at a critical frequency. So, we have two types of approach in doing this testing. We have the operational deflection shape measurement and the model testing. So, for our first approach, we have the operational deflection shape measurement. An ODS can be defined as any forces motion of two or more points on a structure. So, specifying the motion of two or more points defines a shape. So, force dynamic deflection shape measured under a steady state frequency system. So, it is only valid for forces or frequency associated with an operating conditions. For our next approach, we have the modal testing. So, natural frequencies, damping ratios, mode shapes, are determined through vibration testing. Once the dynamic properties of an elastic structure have been characterized, the behavior of the structure and its operating environment can be predicted and therefore controlled and optimized. So, dynamic testing. For my next topic, let me discuss to you the experimental modal analysis. So, experimental modal analysis is an effective instrument for describing, understanding, and modeling the dynamic behavior of a structure. So, it can carried out both to determine the natural frequencies and the mode shapes of a structure and to verify accuracy and calibrate the finite element model. So, also, the experimental model analysis can be used in order to make troubleshooting vibration problems. So, experimental model analysis, it is when a system is excited, its response exhibits a sharp peak at a resonance. So, for the equipment needed to conduct this testing, we needed the exciter to apply known input force, transducer to convert physical motion into electrical signal, signal conditioning amplifier, and lastly, the analyzer with the suitable software. So for the necessary equipment needed in this testing, the first is the exciter. So it can be an electromagnetic shaker or impact hammer. Shaker is attached to the structure through the stinger to control the direction of the force. So the next equipment is the transducer. So piezoelectric transducers is most popular in this testing. Strain gauges can also be used. So for the next equipment, we have the signal conditioner. So outgoing impedance of transducers are not suitable for direct input into analyzers. Charge or voltage amplifiers are used to match and amplify the signals before the analysis. For the last equipment, we have the analyzer. So FFT analyzers are commonly used to analyze signals to find the natural frequencies, damping ratios, and the mode shapes. So, as we can see in this illustration, we can see the general arrangement for an experimental modal analysis. So, we have the elastic cord to simulate free condition. We have the voice transducer, the oscillometer, the exciter or shaker, the signal amplifier, the computer to acquire data and it stores the frequency response function. And lastly, the spectrum or the FFT analyzer. So as we can see also in this graph shown, this is the digital signal processing. This digital signal processing, X of t represents the analog data and X of y represents the corresponding digital record. So for analysis of random signals, input and output data usually contain random noise, as the graph shown in the illustration below. So for solving these random signals, we have the equation x bar of t is equal to the limit of y over t as t approaches to infinity, integral of t to 0, x dt. For the digital signal, we have x bar is equals to the limit of 1 over n as n approaches to infinity, and the sum from 1 equals to 1 over n x of t. So we also define the new variable as x of t. So x of t is equals to y of t. It is also equals to y of t minus y bars of t. So for the mean square value, we have the equation x bar squared of t is equal to the limit of 1 over t as t approaches to infinity, integral of t to 0, x squared t dt. For our digital signal, x bar squared is equal to the limit of 1 over n as n approaches to infinity, and the sum from I equals to 1 over n x x squared ti. So for our root mean square, the value of our root mean square x is equal to the square root of x of bar squared. For, we also have another equation for the autocorrelation function. So the equation of the autocorrelation function is r sub t is equals to x squared and is equal to the limit of 1 over t as t approaches to infinity, the integral of t to 0, t tau times the t tau plus 1 dt. So for our digital signal analysis, we have r sub n delta t is equals to 1 over n minus n, sum from 1 equals to 0 to n minus 1 x sub I times x sub I plus n. So for the analysis also, we have the coherence function. So beta is equals to 0 if x is and f are pure noises, and beta is equals to 1 if x and r are not contaminated at all. So as you can see, we can also see the graph of the typical coherence function. So for determination of modal data from observed peaks, let the graph of h omega be as shown below. So we have here the 4 peak suggesting for 4DOF system. In determining the modal data from the observed peaks, partition into several frequency ranges. Each ranges considered as one DOF system. So damping ratio corresponding to the peak, we have the formula damping ratio is equal to the omega 2i.
Machine condition, monitoring and diagnosis. Vibration in industrial machines. Vibration in machine operations will cause misalignments, cracks, unbalances, and etc. in machine parts. Vibration level will increase until machine failure occurs. Vibration severity criteria. Vibration severity charts are provided by the machine provider. Can be used as a guide to determine machine condition. Vibratory velocity is compared against the criteria set by the standards. However, the overall velocity signal used for comparison may not give sufficient warning for the imminent damage. Machine maintenance techniques. Breakdown maintenance allow the machine to fail and then replace it with a new machine. This strategy is used when the machine is inexpensive and no other damage is caused by the breakdown. Continuation preventive maintenance. Maintenance performed at fixed intervals. Intervals determined statistically from past experience. This period is uneconomical, but the machine is monitored and safeguarded to any downtime. Continuation condition-based predictive maintenance. Replace fixed interval overhaul with fixed interval measurements. Can extrapolate measured vibration levels to predict when they will reach unacceptable values. Maintenance costs are greatly reduced and preventive maintenance. Vibration monitoring techniques. Statistical methods, peak level, RMS level, and crest factor may be used as indices to identify the damage. Machine condition, monitoring, and diagnosis. Vibration in industrial machines. Vibration in machine operations will cause misalignments, cracks, unbalances, and etc. in machine parts. Vibration level will increase until machine failure occurs. Vibration severity criteria. Vibration severity charts are provided by the machine provider. Can be used as a guide to determine machine condition. Vibratory velocity is compared against the criteria set by the standards. However, the overall velocity signal used for comparison may not give sufficient warning for the imminent damage. Machine maintenance techniques. Breakdown maintenance allow the machine to fail and then replace it with a new machine. This strategy is used when the machine is inexpensive and no other damage is caused by the breakdown. Continuation preventive maintenance. Maintenance performed at fixed intervals. Intervals determined statistically from past experience. This period is uneconomical, but the machine is monitored and safeguarded to any downtime. Continuation condition-based predictive maintenance. Replace fixed interval overhaul with fixed interval measurements. Can extrapolate measured vibration levels to predict when they will reach unacceptable values. Maintenance costs are greatly reduced and preventive maintenance. Vibration monitoring techniques. Statistical methods, peak level, RMS level, and crest factor may be used as indices to identify the damage.